what we call the principle of minimum potential energy. So this is the principle that you need to know. This EAS661. Okay. Principle that you need to know in order to solve problems. Okay. So what I'm going to go through with you is how to get to this principle of minimum potential energy. How to get to this principle of minimum potential energy, and which is represented, it is represented by this very concise statement. Okay. And what are the assumptions that we make? The starting point is principle of virtual displacement. Principle of virtual displacement is the starting point, and we go through some specializations until we get to this statement here. And this statement will be called, represented by this equation, will be called principle of minimum potential energy. And this is being used in order to solve a structural mechanics problem. So if you can see from here, del pi p is this capital pi, subscript p is what we call total potential energy. And the total potential energy is equal to strain energy plus another energy that I'm going to introduce to you all. So you need to evaluate strain energy. That's why we go through the process of looking at the equations for strain energy, UP here. So this is strain energy, or later we see this is also called potential energy of deformations. And this is another potential energy. This is potential energy of external load. So the symbol used is U for strain energy or potential energy of external load, and potential energy of deformations, and capital V subscript P is potential energy for external load. And this explanation, of course, is also given in this particular notes here. And this one is, if you go to page, principle of minimum potential energy. So this is where this section 5.4. Okay, section 5.4 is that it gives the detailed explanations. Now I want to go through with you the basis of getting this. So that's why, but you have to refer to that later on to look at the detailed one. Okay. Now, first of all, class, I think these equations, which is the very powerful, I think, statement representing PVD. This is for principle of virtual displacement. And it is applicable for whether the deformation is elastic, inelastic, small or large deflections. It is generally applicable. Okay, so it can be used for elastic, inelastic problem, and it can also be used for small deflection problem or large deflection problem. So this is a very general statement. Okay, so now what we want to look at in the principle of minimum potential energy, the principle that you have to know is we restrict ourselves to what we call conservative system. Okay. So we look at conservative problems. Conservative problems, this is restricted to elastic deformation. So we look at one part of PVD which is restricted to this problem, which we call the conservative problems, and conservative problems dealing with elastic deformations. Because there's a conservation of energy, so it is only dealing with elastic deformations. But elastic here can be linear, it can be non-linear, okay? Because elastic also has linear and non-linear. Only thing is elastic. Whatever you deform, after you remove the load, it goes back to the original shape. That is elastic. There's no plastic deformation. Whatever you deform, then when you let go, it goes back to the original shape. So that is elastic. But elastic can be linear, it can be non-linear. Okay. Now later we will further restrict ourselves to linear problem. Okay. So this is where we want to get. This is the first thing. Our problem is conservative, so it is restricted to elastic now. Okay. Now, if we are looking at elastic deformations, under conservative problem, you look at elastic deformations, then we have strain energy. Okay. Strain energy is energy that stored in the system when you have deformation, elastic deformations. And for elastic deformation, we have this relationship. WP is equal to negative of the work done. Negative of the work done by internal force. Negative of the work done by internal force is equal to strain energy. Strain energy must always be positive. So work done by internal force is negative. So you multiply with negative, you get positive. So this is the relationship that we have for elastic deformations. So if we have this, then we can then relate this to this. Okay. Then notice that we have this, we can put inside here. So when we substitute this into here, then we get delta WE minus delta WP equals 0. Okay. So this is the specialization of principle of virtual displacement for the case of conservative problems. Yeah, this is, it can be conservative, non-conservative, but when we want to specialize it to conservative problem, it can be written in this way. So this is PVD, okay? So this gives you the PVD, principle of virtual displacement, for elastic problem, for elastic deformation problem. Okay. So this is where we relate this delta Wi here to delta Wp for elastic deformation. So we come to this. Now, for conservative problems, for conservative okay, problems or systems, okay, we can relate negative of this to where Vp is potential energy of so for conservative problems, we can relate this negative of delta WE, which is negative of the virtual work done by the external force, to be equal to delta Vp, where Vp is potential energy of external load. So if we consider this into this one, this is already restricted elastic problem. Now we further consider the relations between delta WE and delta VP for which is valid for conservative problems. Then we can get to, then with this you get to consider this, then negative delta VP minus delta WP equal to 0. You get to this equation. Or if you simplify it, you simplify it. So this is the statement of PVD, which is valid for conservative problems, where UP is the strain energy, VP is potential energy of external load. Remember that? UP is strain energy and VP is potential energy of external load. Okay. So what does this equation mean? So del UP plus VP equal to 0. Now, here, before we look at meaning of this equation, so far we represent this class. This is delta. Okay, so please try to be clear about this delta because you have also sigma. Then you have also this del. This is partial differentiation. This is stress, and this is even more stress. Curve on the top there. So when you are stressed, then maybe you are going to write something like this. So this one is not this, and not this, and what is this? So please be clear about this. What we are using here, where we start with virtual, okay, delta like this, and this is sigma when you talk about stress, and this is partial differentiation, partial. So don't write like this. So this one has no meaning. Okay. Okay. Now, they are all in family, but have different meaning that we have covered. Okay, but I want to talk a little bit about this understanding of these terms here. This is, so far we talk about, this is virtual. So this is a virtual work done. Virtual work done by the internal force when the system in equilibrium is giving a virtual displacement. And this is a virtual work done by external force when the system is given, the system in equilibrium is given a virtual displacement. And according to PVD, the summation must be 0. So this comes from this. So this also applies to system in equilibrium. It applies to system in equilibrium. For system in equilibrium, delta of this plus this must be equal to 0. Now, this delta can be understood here as variations, okay? Change, okay? You can understand this delta here at this stage as variation, okay? As a kind of variations or change. Yeah? Change, okay? Change of what? Yeah. Change of what? Change of real displacement. When the system is in equilibrium, already have displacement, which is the real one. So this one is further, you give some change to that real displacement in the equilibrium position. So this, we can understand this delta as having this meaning, okay? So example is, I use simple example, which is a spring, is easy to draw here. Okay, a spring here. So if a spring, we give a kind of if you give it a load here, if you give the spring load here, then this spring will deform. Okay, this spring will deform by delta. So this is the displacement that happened, delta, the real displacement in the equilibrium positions. So this delta that we are going to understand here, variations, means you give a change to this. You give change to this, meaning that you can then further from this state here, you give a change. Change or variation of delta. With the load P acting there, you give a change in variation. So this is the way we can understand this delta. In the beginning, when we started to talk about this, we consider this as virtual. But we can also consider this delta here as a kind of variation or change of real displacement delta in the equilibrium positions. So with that understanding, so we can come to a definition of this. What does this statement mean? Okay, what does this statement mean? The change in summation of this plus this equal to 0. So what does this mean? Remember, we are talking about a system in equilibrium. And this one can be understood as change. Change in what? Change of real displacement in the equilibrium positions. Okay. So this says that, I think here, let me write it down. So these equations, that equation represent that equation, it represents the meaning. This is the note. So during any, okay, at B virtual displacement so during any admissible virtual displacement from the equilibrium positions, so the sum of the change, okay, in strain energy and also potential energy of external load. Yeah, the sum of that thing is 0. So that statement means this. So we are talking about equilibrium. So why we have change of the sum of this is because you give the system virtual displacement. So if you give a system a virtual displacement which is kinematically admissible, then the change of sum of this state energy and potential energy and external work must be equal to 0. So that is the meaning of that statement. Okay. So now we give a term, we give a name to this summation of UP plus VP. We call this another symbol pi P. So this pi P is called total potential energy. Total potential energy. Okay. We call this total potential energy. So when we replace that with this symbol, then finally we have this now, when we talk about change of something equal to 0, the change of something equal to 0, you can understand this as a kind of, if you try to imagine this pi p as a function, then the change of that functions equal to 0. Okay, so the change of functions equal to 0, meaning that there is a point. There's a point. Okay, if you have this is a total potential energy, and this is displacement. And if you draw the graph, okay, so this is the situation here. This one means this at this particular point, the change in total potential energy is 0. So, but we know that the change, these situations, this can also represent the situation like this. Yeah? It can also represent situation like this. If you have a pi p, and this is displacement, it can also represent like this. This also means change is 0. That point also can be, this can also represent these situations. Change in the function equal to 0 means you have a maximum point, minimum point, or you can have a inflection point. Remember in calculus we study dy dx equal to 0. Dy dx equal to 0 can be like this, it can be like this, it can be like this. So now at this stage, okay, if we want to apply it to a situation maybe like this, maybe like this, maybe like this. So this statement here is called, principle of stationary. Principle of minimum potential, principle of stationary potential energy. Stationary means stop there. It can be like this, it can be like this, it can be like that. Okay. But for our EAS661 here, for your course, what you need to solve is a particular class of problem out of this, which we call stable. Okay. Stable elastic. For stable elastic problem, Okay, then we have this situation. For stable elastic problem, total potential energy is minimum at equilibrium position. So this is the case for stable elastic problem, equilibrium. This is for the case of unstable elastic problem, and this is for the case of neutral, okay, elastic neutral positions. This is stable equilibrium, this is unstable equilibrium, this is neutral. So we are not going to go into this problem. Our focus is on this particular type of problem here, okay, where the pi p is minimum, which means we are restricted ourselves to the problem of stable elastic equilibrium. Stable elastic problem, okay? Stable. Equilibrium can be have stable, unstable, and neutral. Later, when we go to 663, we have equilibrium can be stable, unstable, and neutral. So what we are going to apply to is stable elastic problem, meaning that the situation that we have is total potential energy is minimum at equilibrium positions. Okay. So with this, if we restrict ourselves to stable elastic problem, where the total potential energy is minimum, so we call this principle of this is principle of minimum, okay, potential energy, or we call it PMPE here in our lectures. This is principle of minimum potential energy, which is we restrict ourselves. We apply that principle only to stable elastic problem. Then the total potential energy is minimum at equilibrium. So this is classified as principle of minimum potential energy, or PMPE. Okay? PMPE. So PMPE is represented, the principle of minimum potential energy is represented by this statement here. Del phi p equal to 0. So before I end today, I think we are now almost 1 o'clock now. So we want to understand the meaning of this principle. Okay. This is the statement for So I would like to end with what is a statement? What does this mean? What does this mean? So it means of all. Okay, I write it down here so that you can understand, appreciate this. Statement is short like this: of all possible kinematically admissible, okay, of all possible kinematically admissible variations of all possible kinematically admissible displacement shape or displacement configurations. Configuration is, we can understand as shape, displacement shape. So there are many possibilities. Of all possible kinematically admissible displacement configuration that an elastic body can take up. I mean, there are many possibilities that the displacement shape that a problem can take up, curve like this, curve like this, or curve like this, or any other curve. As long as they are kinematically admissible, there are many possibilities. And out of these so many possibilities, the configuration out of these so many, the one that is going to satisfy equilibrium, not all satisfy equilibrium. They are possible only. So the configuration which satisfy equilibrium makes the total potential energy assumes a minimum value. So this is what we can use to represent the meaning of this statement. Of all possible kinematically admissible displacement configurations. So if I represent this using this graph, so this displacement represent all possible displacement, any value that you can give to the elastic body, and it must be kinematically admissible. Then the one which is going to satisfy equilibrium is the one that when you substitute into pi p, it gives pi p a minimum value. So that is the meaning of this statement. So of all possible kinematically admissible displacement configuration that an elastic body can take up, the configuration out of many of these which satisfy equilibrium makes the total potential energy pi p assumes a minimum value. Okay. So that is what I would like to conclude. And when we go to apply this, so we assume, equilibrium, we assume a displacement, then we try to apply this, and then to find whether the pi p is minimum or not. Okay, so that is the basis of principle of minimum potential energy in solving a structural mechanics problem. Okay.